In Chapter 3, we're going to discuss the physical and mechanical properties of dental materials. We will define primary and secondary bonds and give an example of how each determines the properties of the material. We'll describe the three forms of matter and give a defining characteristic of each. We will define density and explain the relationship of density, volume, and crystalline structure. We will define hardness and describe how hardness contributes to abrasion resistance. We will define elasticity and give an example of when elasticity is desirable in dental procedures. We will relate stiffness and proportional limit and describe how these properties apply to restorative dental materials. We will define ductility and malleability and explain how these characteristics contribute to the edge strength of a gold crown. Explain the difference between toughness and resilience. We will define brittleness and discuss how this property applies to restorative dental materials. We will define viscosity and thixotropy and describe the clinical significance of each. We will differentiate between therapeutic, preventative, and restorative materials. List and describe the three main types of restorative dental materials. Describe the reaction stages a material undergoes to acquire its final state. And we will describe the variables in the manipulation of a material. As far as physical structure goes, dental materials are built from atoms and molecules. So we know probably from our science, physical science back in high school, that two atoms combined together make a molecule. We are going to discuss two categories of bonds. Primary bonds are strong bonds, and then secondary bonds are weaker bonds. An example of a secondary bond is a hydrogen bond or water, those kinds of bonds. There are three types of primary bonds. We have ionic. Ionic will give electrons to another atom. These bonds are easily broken and very brittle, and these are poor electrical conductors. Another type of primary bond is the covalent bond. Anything co to me means share. So these atoms share electrons in their outer shell. They're strong and they have a high melting point, and they are not easily broken. And then metallic bonds is the last type of primary bond. They have a shared lattice of positive electrons which are attracted to a negatively charged cloud of electrons. Like I said, the secondary bonds are weaker than primary bonds, and this weakness can often lead to deformation or fracture. There is no sharing or transfer of electrons that occurs in a secondary bond. The three states of matter are solid, liquid, and gas. A solid has shape and volume, and it has the strongest attraction between atoms. Liquid has volume but no shape, and gas has no volume or shape. So most materials that we use are mixtures of more than one state of matter. For example, like if we're using plaster in the lab, that's a combination of a solid, and then the liquid is the water that we mix with it. Density is a measure of the weight a material has compared to the volume of that material. Again, in these chapters, at the very start, there's a list of all of the key terms. And if you familiarize yourself with those vocab words and have an understanding of those, it will help you immensely with these chapters. Hardness is the resistance of a solid to penetration. So this will define the material's resistance to wear and abrasion. So you can imagine that this is very important for dental materials. They obviously withstand a lot of stress, so they need to be hard. The new hardness is the value that's usually given for dental materials. And enamel and porcelain both are hardest materials and are more resistant to being scratched than other materials in the mouth. Elasticity is exactly that. If you think of elastic will stretch out and then it will go back to its original form. So what elasticity is the measure of a material to recover its shape completely after deformation from an applied force. So this is important for impression materials. We mix up materials, we put them in the mouth and they stretch around the tooth, and when we take it out, we want it to maintain its shape. So impression materials are important, as well as ortho wires and springs that are deformed, and the force that they generate in returning to their original shape is what moves teeth. Stiffness is the resistance to deformation. So this is measured by Young's modulus, which is an elastic modulus, and the restorative materials should have a modulus that is compatible with tooth structure. So we want those materials to resist deformation just like a tooth can. Ductility is the amount of dimensional change a material can withstand without breaking. So if you look at the screw below, you can see that it's being kind of stretched, and it'll stretch until it breaks. So if something is ductile, it can be stretched quite a lot before it breaks. Tensile stress, which I talked about in the last chapter, is that ability of a material to be stretched, just like tinsel on the Christmas tree. Gold is very ductile. It can be elongated close to 20% when it is under tensile stress before it breaks. Materials with poor ductility are classified as brittle. The material will tolerate very little strain before it fractures if it's put under that type of stress. Malleability. I think of a mallet when I think of this. So this is the ability of a material to respond well to compressive stress. So it could be hammered into a really thin sheet without fracture. So I think of a mallet hammering material, and it's able to go into a super thin sheet before it fractures. And if you look at these coins, that's what they've done, is kind of pound them out. Edge strength this is important for edge strength. So gold, you want the margin of that crown to be able to be super thin, so it has a really nice relationship with the tooth. So gold has a really nice ability to be malleable and have that nice thin border against the tooth. So edge strength of a restoration is a combination of malleability combined with ductility, being able to be stretched as well as being able to be hammered to a thin sheet. Amalgam does not have good edge strength, but gold does. Toughness is the ability of a material to absorb energy without fracture. Restorative materials must exhibit toughness. This toughness will limit the failure of that restorative material on posterior teeth, because they're going to withstand lots of chewing force and abuse. Small amounts of deformation can cause fracture. Gold and ceramic are very tough materials. Resilience is the amount of energy a material can absorb without permanent deformation. So they can absorb the energy and be resilient and go back to their normal form. Impression materials and orthodontic wire must be resilient. We talked about viscosity in the last chapter as well. And what is viscosity? It is a liquid's resistance to flow. So it gives us a value for how thin a fluid is. That would be low viscosity. And if a material is really thick, it's going to have high viscosity. Thixotropic materials are liquids that flow more easily under mechanical force. An example I can give you of this, excuse me, when I was in dental hygiene school at UMKC in 1991, we did not dispense fluoride in the way that you guys do today. We used the foam trays, and we would put this liquid or gel, more like a gel, into the foam trays, and we would put it in the patient's mouth, and we would have them bite on the tray, upper and lower, and we would tell them to kind of grind their teeth together for the amount of time that we kept that in their mouth. That movement of their teeth would allow that material to flow more easily under those forces and get in between and around all of their teeth. That was a thixotropic gel that we were using for fluoride. Now, I told you dental materials are classified into 3 categories. We have therapeutic materials, and that is exactly what it sounds like. This is used in the treatment of disease. So therapeutic materials would be if we use something for the bacteria, when we place a chemotherapeutic agent in a deep pocket to try to help with the bacteria, that would be therapeutic. A preventative material would be directed towards prevention of oral disease and promoting oral health. So with this, I would think fluoride, sealants, things like that. And then restorative materials obviously are used to restore or replace lost tooth structure, teeth, or oral tissue. And these materials can be used for short or long-term use. Metals have properties such as strength, ability to conduct electricity and heat. They're malleable, like I said, can be pounded into a thin sheet. They're ductile, they can be stretched, and they have luster. We can make them shine. Ceramics are generally rigid and brittle and melt at a very high temperature. They are poor conductors of heat and electricity. Polymers can be flexible. These are typically used for dentures. They're easily shaped and rubbery, but also rigid and difficult to mold. Some of the reactions that can happen when we mix components together are they can either have a physical reaction, which would be such as, like evaporation or cooling of a liquid. Chemical reaction would be a creation of new primary bonds. So most reactions of 2 components result in a solid structure. I think of that when I think of us mixing our dental stone with water. We mix it together, and if you allow that to set, it will become a solid stone. And as it does that, it gives off heat. It warms up and it gives off an exothermic reaction. And that is one way we know when our stone is set, it will be cool to the touch. That exothermic reaction will stop. And that's how we know that our stone is cured. There are different types of reactions. We have a chemical set, and this is set through the timed chemical reaction of a catalyst mixed with a base. And in a chemical set, we as the clinician have very little or no control of the time. You usually have a set amount of working time, like a couple minutes before that material is going to set. If something is light activated, it uses our blue curing light as the source to initiate that reaction. So this gives the clinician a little bit more unlimited working time. However, the ambient light or the room light can cause the material to begin to set, so you can be limited a bit that way, but you do have more control over your working time. A dual set begins with the initiation of the blue light or curing light, and then it'll continue with a chemical set reaction. This gives us more control of the working time again, and it will assure complete setting in deeper or more difficult to access areas. One area that dual set is very helpful is veneers. If we are cementing those with a resin that must be cured, we are going to be light curing through the veneer, and we want the chemical to also cause curing so that underneath that veneer, we're sure that we're getting a solid and complete set. Same like under ortho brackets. We can cure around the edges, but we want to make sure that it's cured all the way through. So a dual set is ideal for both of those applications. Timing for a procedure. Understanding the amount of time we have from start to finish is very important. So the manipulation stage is that time that includes our mixing time of being able to mix that material together, and the working time is how long I have to work with that material in the mouth. So the reaction time includes not only that initial set, but also final set. Many materials will appear to be set, but they need a little bit more time to reach their final set. Each material has a set mixing time, working time, and setting time that is usually given to you on the container or from the manufacturer so that you have a good idea of how much time you have to work as far as mixing that to that nice homogeneous mix, getting it in the mouth, letting it set in the mouth and pulling it out, and then how long, let's say I'm doing an impression, how long until the final set. So all of those things are important. Different variables with manipulation are the ratio of components. In today's world, things are done so nicely and in pre-measured packets or in the little guns that do exact amounts that need to be mixed together. When I was an assistant, we eyeballed it, or we used measuring spoons or plastic cylinders, things like that. And there was always room for human error. So ratio of components is very important. Other things to consider are external variables, the temperature of the material when we're mixing it, and the room, the amount of humidity in the air. All of this is going to affect how quickly or slowly materials are mixed. The warmer something is, the faster it's set. So if you're wanting to mix your impression material and have a little bit more time to work with it because we're newbies at this and we don't want it to set up before we get it to the mouth, we would want to use colder water because that's going to give us more working time. So those are all things to think about. Shelf life. If a material is past its shelf life, it may not react in the way that it should or not as effectively as it should. So we want to make sure that we are storing our materials in a dry, cool, usually dark area is best for most materials. Manufacturers will provide you with the information on where they need to be kept, when their date is, and we want to pay attention to that when we're, if you're in charge of putting stock away in your office or at our clinic, you always want to rotate and bring the oldest material forward and put the newest material to the back. In summary, a material's characteristics are defined by its physical structure. Materials are available in a variety of forms, and we always want to pay attention to the manufacturer's instructions because they are essential for us to produce the best results with their material. The success of these dental materials is directly related to the choices that we make in selecting and manipulating the components of those materials when we're working with our patients as well.